Okay, we've already learned how to do volume if you take a curve and you rotate it around an axis. But now we're going to do the same thing. Take a curve, rotate it around an axis, but now instead of finding volume, we're going to find surface area, the outside covering. Okay, so that's what we're doing now. Before we find surface area, we need to learn how to find the length of the curve. Length on a straight line is easy. Length of a curve, which changes slope and all that stuff, is a little bit different. And so that's what we're going to do now. Oh, you're like staring at a blank screen. That's boring. Hold on, I didn't prepare ahead of time to get my pretty colors. Okay, now I got pretty colors. So, lengths of a curve, or arc lengths we call it. Arc lengths. Okay, so that's what this is going to be about. And you will be doing some calculus involved with just the arc length, and then we're going to go from arc length to surface area, which, by the way, we're going to use the same type method we did when we were doing cylindrical shells. So when we get to that part, which we'll do in class, it'll be very similar, but the length of the curve is a little bit different. All right, so just so you know, the formula is, and there's a beautiful proof in your book which explains why this is what it is. But the length of the curve, which usually they indicate by the letter S, is the square root of 1, and it's always the number 1, plus, now I'm going to use different notation, but it's either, now the prime, y prime, which is the derivative, or square root of 1 plus x prime. So basically, oh my gosh, I wrote x squared. Basically, whatever they give you in terms of the equation, you use that. So if they give you like y equals x squared, then you're going to put x squared, you're going to do the derivative of that. If they have x equals y to the third, then you're going to do the derivative in terms of y. Okay, so it doesn't really matter what variable they give you, you're going to use that expression, so you'll never have to change into a different format. You know, some of those, if they gave you y equals x squared, you might have needed x by itself, and you would have had to take in the square root. That's never the case with arc length. So you use whatever you have there, whether it's x prime or y prime. So it's basically your function, the derivative of the function. So right now we'll do an example where it's, a lot of times they'll do that, f prime of x, they'll write it like that also. Oh, sorry, it's the derivative squared. I told you about the derivative part, but not the squared. Okay, of whatever your function is. So that little prime symbol, that little apostrophe, means derivative of, and then it's the squared. And it's the square root of that. So the square root symbol is over everything. That gives you the length of the curve, and when you use calculus, it's going to give you the length of whatever your boundaries are. So if I want, what's the length of the curve between where x is 0 and 5, and that curve might be going all kinds of ways between 0 and 5. And so the calculus is going to add together basically all the little individual little areas all the way across. So that's kind of what you're doing in a general sense. So let's use the formula and get cracking here. So I'm going to scoot everybody up with my little scooty. Yeah. Okay, so let's start fresh with the problem. We need some pink in here, some purple. Whoop. There we go. Okay, so let's say we have, and this is one of the examples in your book too, which probably isn't doing you any favors, but whatevs. Whatevs, I said, because I'm so hip. Y equals x to the 3/2 power. That's hard to read. Y equals x to the 3/2 power. That's my curve. All right, and I want to know what's the length of that curve between where x is 0 and 5, and so we indicate it using brackets like that from 0 to 5. So you can graph it if you want to look at it. It looks sort of like a parabola from 0 and 5. It kind of goes like that. And so in order to find the arc length, I'm going to use calculus. I'm going from 0 to 5. And it's the square root of 1 plus the derivative of that expression. So now before I can fill in the rest of this, you have some work to do off to the side. So off to the side here, I have x to the 3/2 power. I have to take the derivative of it. Here's what's hard. Your brain has been doing antiderivatives all this time. This is regular derivative. Old school calculus 1 regular derivative. That's where you took the exponent, brought it forward, 3/2 x, and you subtract 1 from your exponent, which in this case is 2/2. So 3/2 minus 2/2 leaves us with 1/2. And that's our derivative, okay? So that's y prime, in other words, or f of x prime. And so the formula says I have to take that, so I have 3/2 x to the 1/2 power, and I have to square it, because the formula says square the derivative. Okay, so I have all that stuff going on. You have a lot of cleanup you have to do. So from 0 to 5, square root of 1 plus. Now let's go ahead and square this expression. 3/2 times 3/2 is 9/4. X to the 1/2 power, when I square it, x to the 1/2 times 2 is just x to the first. That's just x. Okay, so cleanup's going pretty good. Continue the cleanup, because in calculus we don't work with radicals. We use exponential notation instead. So we have 9/4 x to the 1/2 power, and I'm ready to do my calculus, my antiderivative. Okay, which is antiderivative here. Add 1 to your exponent. So I'm going to add 1, which is 2/2. And I get 1 plus 9/4 x to the, when I add 1/2 plus 2/2, I get 3/2 power. And then you divide by your new exponent, which is 2/3. Now, this one, be really careful, okay? Oh, wait, I didn't put my 1 here. There's 1 plus 9/4 x. When you did chain rule back in Calculus 1, and you were doing derivatives with something inside parentheses, you had a last step of multiplying by the derivative of what's inside. Well, now we're going backwards. So instead of multiplying by the derivative of what's inside, you divide by the derivative of what's inside. Well, the derivative of what's inside here is 9/4. Okay, I just had to pause the video because my phone rings, so I don't know where I was. But anyway, all right, so I was talking about times the derivative of what's inside. The derivative of what's inside is 9/4. When you divide by a fraction, you flip it and multiply. Okay, so that's everything that I have inside the radical. That's the calculus part, so I don't want to write that little integral symbol anymore because I've already done my calculus. But I do have a lot of cleanup to do. For the love of all that's holy, people, do not start plugging in 5 and 0. Do some, I mean, you can, but do some cleanup first. Oh, you know what? There's not a lot of cleanup we could do. That's kind of gross. All right, well, I would at least multiply the 4/9 and the 2/3. That gives me 8/27. Now, here's a little trick. Because you're multiplying 8/27 times this whole chunk, then it works like pi did on all these other problems. And you can kind of take that out. Sometimes it makes it a little less chunky inside there. It's a little easier to see what's going on. Okay, so that's what I have. 2 to the 3/2 power. And I got to plug in my 5 and my 0. So it's not going to be pretty, okay? There's going to be nothing pretty about this. It's not going to give you whole numbers. It's just, it's going to be gross. But that's okay. We ain't scared. Okay, it's time to plug in 5. So when I plug in 5 for x, I get 5. Well, you got 5 times 9. So I get 45 over 4. All right, 1 plus 45 over 4 to the 3/2 power. So it looks like, oh my gosh, what am I going to do? But clean up. Get a common denominator here. So we have 4/4 plus 45/4. Look at there, a perfect square. 49/4. Both of those are perfect squares. If it's been a while since you have used fractional exponents, remember the bottom number tells you what root you're going to take. So this says do the square root of that fraction and then cube the answer. So that's what I'm doing here. 49 over 4. Square root of that, square root of 49 is 7. Square root of 4 is 2. So I get 7/2. And now I have to cube that because that's my numerator. 7 times 7 times 7. I forget what that is. 343. And 2 cubed is 8. Okay. So that's what I get when I plug in 5. Now, I'm not going to forget about that little 8/27. Okay, Preston, you thought I was going to forget, but I didn't. All right, so I'm still leaving that on hold. Okay, because this is what I get when I plug in 5. Now I have to do it all for when I plug in 0. So I get 1 plus, okay, this is nice because 9/4 times 0 is just 0. And so I get 1 to the 3/2 power, which is just 1. So it's minus 1. So I'm going to put that over here. Minus 1. I'm going to go ahead and put 8 over 8 because I know I'm going to have it. Okay, and subtract 343 minus 8 is 335 over 8. Okay, and then, so I've plugged in both my numbers. I subtracted those two. Now is when I have to apply this little times 8 over 27. Is everybody with me here? Your 8's cancel. So your final answer is 335 over 27. That's the arc length. That's the length along that curve between 0 and 5. So it's just over 12.4 if you kind of did that in your calculator. So that's arc length.